All right, we are recording. Beautiful. So, I made a huge mistake last Tuesday, and I could not figure out this problem for the life of me, and we just had to move on because I forgot a crucial concept. Okay, so the problem we tackled last Tuesday, well, just 2 days ago, was this cable problem. All right, I'll just redraw it right here. 50 kips. So we have a cable that's supported on both ends right there. This entire height is 10 feet. And we have this span right here. This from here to here is 10 feet. Got 15 feet right here, and another 10 feet right here. Right. Um, so there are two pins right here. So we're gonna have a reaction right here in the y direction. We have a reaction here in the x direction. And same thing over here, ry. I'm gonna call this b, and then rx b. So we're just gonna call this point A, point B. We'll call this point C and point D. All right. So rxa, rya. So this is a cable. The thing about cables is that they only have one reaction force, and that's an axial force. Um, more commonly referred to as tension. So my mistake, whenever we cut this in half, was I thought there was an axial force, a shear force, and a moment reaction. No such thing. There's only an axial force, which is the tension in the cable. Right. So if you think about it, what's a prop I could use? All right, we're just gonna use this thing, right? So we just have a cable, right? I pull on it, and it puts a little bit of tension on it. If I put some shear on it, it just bends. It just bends. It like it doesn't deform. There appears like just some sort of bend in it. But if we had a beam, if we put a shear force on it, then it'll deform. And it's different because see here, it still keeps its general shape, but it's just slightly deformed a little. But in a cable, it changes shape completely. There's really no resistance when there comes to a shear force or a moment force. So cables, they always have one reaction force, and that is tension. So let's just start at the beginning. We're gonna solve. We're gonna solve for these moment reactions, or these reactions right here. So very simple. Start with forces, summation of forces in the x direction. We're going to assume right is positive. And we have 2 Rxa, that's going to the left, minus Rxa. And we have 1 going to the right, Rxb plus Rxb. And it's going to turn out to Rxa equals Rxb. Can't really do anything right now. So let's move on. Summation of forces in the y direction, and we're going to assume up is positive. We have 4 of them, rya, going up, rya. We have this 50 kips minus 50 kips because it's going down, minus another 50 kips, that's going down, plus ryb. Fun stuff. We move rya and ryb to the other side. We get rya plus ryb is equal to 100 kips. Right? Can't really do anything with that. We could take summation of moments right here, but it honestly doesn't really, like, you'll get somewhere, but you can do it in other ways. So we're just gonna skip that real quick. And we're just gonna cut this cable in half because you can do that with cables, right? So we cut in half right here. And then we have this half of the cable. Have E, we have B, we have E. I'm just going to call this point E. And then you have, that's not right. And you have 7.5 feet right here and 10 feet right here. This is 10 feet deep. We have a reaction in the Y direction, reaction in the X direction. We have the 50 kips down here, and we have only one internal force, and that would be tension. I'm gonna just call this tension at E. Right? So what can we do with this information? Well, let's start taking summations. Summation of the forces in the X direction, where right is positive. We have negative TE, tension at B. And then we have RXB up here, plus RXB. And we just get TE equals RXB. All right, so we can't do anything with that information. That's fine. We'll just move on. Summation of forces in the Y direction, up is positive, equals, let's do negative 50 kips, because that's going down. And this RYB right here is going up, so plus RYB. So that would result in, yeah, so that would result in a RYB equals 50 kips. Fun stuff. All right, so where do we go from here? Well, now we can take summation of moments, right? So summation of moments at E. Assume counterclockwise is positive. So we're going to take them at E. So right now we want to know what RXB is. So we're going to take them at E, so we don't really care about tension right now. Well, you can actually just solve for tension and then set it equal to RXB, you know, just use this equation right here. But let's just make it harder on ourselves. Tension at E. So we're going to take summation of moments at E. So we have this force right here, 50 kips. It's going down. It's going to go clockwise. So minus 50 kips. How far away is that from E? That's 7.5 feet. Right? 7.5 feet. You have RYB, which we figured out was 50 kips, and that's going to go up. So that's in the counterclockwise direction. Yeah. So that would be plus 50 kips. Times, we're going to add 7.5 and 10. That makes 17.5 feet. Right. And then RXB right here, that's going to the right. So take the orbit right there. That would be clockwise. So that would be negative. So that's a minus RXB. And that would be 10 feet away from E. Fun stuff. Let's start. Let's just solve this equation after I make some room. So 0 is equal to minus calculator. So we have minus 375 kip feet plus 875 kip feet minus RXB times 10 feet. Right, so we can move RXB times 10 feet to the other side. That becomes positive RXB times 10. set that in. That's equal to and be around 500 kip feet. All right. Yeah, 500 kip feet. And then we just divide by 10 feet. RXB equals 50 kips. So we got another 50 kips, but that's fine. We can work with that. I also wrote the problem this way so that it would be, we would get nice numbers. Just to simplify it, but you know, tests might be more complicated than this, so this is just
I wonder
to
if we're gonna get
establish a basis.
I wonder if we're gonna get nice numbers on the exam.
Unsure.
Fingers crossed, man. Fingers crossed.
All right, so RXB is there's 50 kips right here, and so that means tension at E would be 50 kips. So 50 kips all around, right? Fun stuff. But what can we do with this, right? Well, one thing you can do with this information is, well, 50 kips. One thing we can do with this information is figure out this angle right here, you know? We can use the 50 kips and 50 kips. We can, well, I'll just do that right now. Right, so we
these
can.
type of problems, aren't we normally just looking for the tension?
Yeah.
He's never asked for the angle, right?
Well, you can find the angle if he ever asks for it.
But he hasn't before, right?
I don't remember.
Not that I know of.
Yeah, but you can find the tension, but remember vectors, you always have a magnitude and a direction, so finding all components of a vector would help.
The angle is 45.
Yeah, well, you're jumping the gun there, my guy.
Well, it's because it's the x is 10 and the y is 10, and that means it's an equal. It's whatever I think isosceles is the term, but yeah, it's an isosceles right triangle, which means it's 90, 45, 45.
Yep, you are correct. But let's use the forces because, as you'll see later, you can't directly. Sometimes you just can't use these values right here. Sometimes you have to use the force vectors. I'll get to that in a bit. But you know, 50-50. Want to find out this angle right here. So this is just a representation of the reaction angles of the reaction forces. So we have the 45 degree right there. Well, we don't know what the degree is, and I forget what this term is called, but in trigonometry, these angles would be the same. So 50-50, SOHCAHTOA, you remember SOHCAHTOA, SOHCAHTOA. Right? We would use tangent because we have the opposite and the adjacent. We currently do not care about the hypotenuse, so we use TOA. Tangent of theta is equal to opposite over adjacent, 50 kips over 50 kips. Right, theta is equal to inverse tangent of 50 over 50, and tangent theta would equal 45 degrees. And then you can also use Pythagorean theorem to determine how much tension is right here, right? So you have these two vectors, right? You know the angle of the reaction vector, but you want to know how strong it is pulling, right? So you just think back to vectors, you know? You have these two vectors, but what's the overall vector right here? What's this vector? Right, so Pythagorean theorem c squared equals a squared plus b squared, you know, so c is equal to square root of 50 squared plus 50 squared, and that would equal, let's see, that would equal 70.71 kips. All right, so what does this mean? Well, now we have this cable. I'll just delete this first bit right here. So we have this cable right here. We have this cable, right? And then we have a force acting down this way, a force acting down this way. Right here, well, more realistically, along this entire cable right here, there is a tension force, internal tension of 50 kips, right? It has 50 kips of tension inside that cable. And in this part of the cable, there's 70.71 kips of force of tension. Right, so that's what sort of those numbers mean, and why it's important to know your vectors and stuff.
I have a question.
Go for it.
How do you know that the tension at point E is equal to RXB?
RXB. Well, wherever we cut it, right here, there are only two horizontal vectors in the free body diagram. So they would have to be equal to each other. Does that make sense?
Yeah.
Okay, cool. So why do we go the long way? You know, why didn't we take this, why didn't we just take 10 feet and 10 feet? Well, what if you had, parabolic shape, right? What if you had a parabolic shape? What if you don't know, you know the entire span of it, right? What if you only know the entire span? What if it's a parabolic shape? What if you just know these two measurements? You know, let's say this is like 23,000 feet. Is like 377 feet or something. Like, how do you know exactly what the angle is right here? You really can't know because it's always curving. The angle is always changing. So that's why you would have to you have to use the reaction vectors in order to figure out what angle is happening there. Right? So you can't like just cut this in half and figure out this angle, because see, this angle, it's much shallower than the actual angle that's trying to go for. You're trying to be a tangent to the cable, you know, and the only way you can figure that out if there's a curve and you really don't know what you're doing is to find the reaction vectors and then use Pythagorean theorem to do that, and using inverse tangent. And just another side bit, why do we have a parabolic shape? Well, it usually comes from a linear load across the entire body, the entire span, and this is usually what's present in bridges. You see a bridge, you have two towers at the end, you have the deck, and then you have a parabolic shape right here, and some just additional cables to hold the bridge together. Right, so instead of using 2-point loads like in our previous example, in this problem you would use the linear load. Use the linear load in your calculations, and hopefully you can do that. If you went to Tuesday's lecture, well, not lecture, review, I went over some linear loads there. Right, any questions?
So in this particular case, would there be any trigonometry? And if so, how would that work since you don't know the angle?
Right, so there would be two reactions again. And then so you would obviously use trigonometry with these two reaction vectors if we were to cut it in the half right here. So you get this sort of free body. There would be a reaction right here and a reaction right here, and you use trigonometry in with these two vectors. So you have a measurement right here and a measurement right here, tension right here, and then you can take summation of x, y, and moments to figure out these two reactions, just like we did in the previous problem, and use trigonometry there to figure out angles and overall magnitude. Yeah.
Well, I thought the angle is constantly changing. So how would you find an angle?
Well, we can find the angle right here, right? I mean, like, it doesn't constantly change in one position, right? Like, if you have a set position, then it's going to always be that angle in that one position. As you move through the cable, it will be changing, but at one point, sort of like in calculus, taking what is it? Just differentiating equation to find the slope of a of an equation at a certain point, right? So it will be constantly changing throughout the entire cable. So I don't know if there's math to like find these angles, but at this particular point, there are these specific reaction vectors, and you can find the angle that's right here, that's tangent to the cable, right at that point right there.
Right, but then at the end of the day, we're probably just looking for like the tension at the cut point, like at that.
Yeah.
That's
at the
what
cut
you're
point.
like. Yeah.
Right there. So you can take it a step further and find the tension in the cable right here, right at that one point.
Yeah, and I think this goes back to what Alejandro was saying, because I flipped back to like the structural midterm review, and now I see where if I had properly gone through my notes, I would have seen that where it was only tension, that there's no, when you cut, there's no what is that called, V and M going on at the C. It's only T. I see that now. And then we stopped right there once we found tension at like the cut point. We pretty much stopped that. But then he did. I see what he also said, Edison, with like when it's a parabola and there's a line mode.
Yeah. All right. Anything else? Any other questions?
So if you're calculating the tension at the cut point, you would use the angle that's closest to that.
Well, if you think about it, so let's say these are perfectly level, right? If you think of a parabola, there's one point where the slope is 0, right? Where it's completely horizontal because it's changing from here to here at a constant rate, constant decrease and then constant increase. But there has to be like one point where you know the angle's 0, which is pretty cool because now you have a set like baseline for your calculations. That's a base angle that you can calculate from, right? So you would cut it in half, and then right here the angle would be 0, and then you can use that. to aid in your equation solving. Did that answer the question? Your question?
Um,
You ready to eat, bud?
But yeah, I'm getting it. I definitely see, like, we're looking at the tension at the cut point. You would still go through like the forces in the X and the Y, take the moment, then cut it in half, and then re-go through forces in X and Y, and then that last moment calculation would give you the tension at the cut point. Yeah. So I hope I think we're all hoping that's the extent of a cable problem, that it shouldn't really go past that point. Really.
Yeah. That's what I'm hoping as well.
Yeah. Cool.
Any other questions anyone has? All right. Let's move on, I guess. Right. So the last topic I wanted to go over was, oh boy, everyone's favorite thing.
Hang on, Ali, did you say something earlier? Because you were muted. Oh, okay.
So we're gonna go to everyone's favorite topic, U value, right? And then we're gonna, like I had a thing. Oh well. Here, let me see if I can pull up the slide. Well, first let's go back to U value. So let's say we have a wall. I'm just gonna use the wall from the midterm. Midterm. All right, there it is. So we have our wall. So I'm missing something. Yeah. Right. So we have our wall. We have an outside air film. I can type. We have an outside air film. We have a brick veneer. Polystyrene insulation board. We have plywood. We have that insulation junction with wooden pine studs and a final layer of gypsum board. This one is 5/8 of an inch. We're gonna do 2x4. This is 3.5 inches because you know the actual dimensions of a 2x4 is 1.5 by 3.5 inches. We have a plywood sheathing, 1/2 of an inch. Oh gosh, 1/2 of an inch. Insulation board, that would be 2 inches. Brick veneer, we have 1.5 inches. And again, I forgot the inside air film. Right, so this is just going from left to right, outside in. We have the bricks. We have the insulation right here. Jeez. But I'll just bricks right here.
Santos, why does your video look like that?
My video look like what?
I think earlier it was a little glitchy, probably because you were just moving a lot. It looked like a static television or something.
I don't know, because it's clear now. Oh, you guys have been clear to me the whole time.
Yeah, now you're looking at HD, high definition.
You see all the sweat from earlier dripping off my face.
Right, so we did our calculations. We have, okay, so outside air film. Oh, geez, I'm gonna have to, because I don't feel like looking these up. I'll just get them directly from the midterm. So the R value of brick veneer was 0.15. Pine studs, the R value is 3.56. And these were just the answers for the midterms. So honestly, they might not be accurate, but these were the answers that Van Leidingham put out.
Right, like when you go check the midterm in Blackboard, this is what comes up.
Right, yeah.
I remember.
Gypsum board was 0.56. I get the 10 from, oh. I assume 10 was the insulation. Plywood is 0.62. The bat is 15.
Would there be an air gap?
This wall assembly doesn't have one, but it might. If you have an air gap, the R value is always 1. So just something to keep in mind. Air gap is always 1, no matter the thickness too. Surprisingly. All right. Well, I guess I do have to look this up. R values. Let's see. So R value for outside air film would be.
It's 0.17 according to the
0.17.
from Tuesdays. So I'm pulling these numbers from Tuesday.
Okay.
And
Point
then
68.
yeah, you got it. Nice.
So these numbers might be a little bit different from. These numbers might be a little bit different from yesterday Tuesday's thing, but these are just the numbers we're gonna work with. All right.
Yeah, because I noticed that on the bat installation, I remember from Tuesday was you put 13, now it's 15.
13, yeah, but on the.
Yeah. So now you're pulling this straight from the midterm. So
straight from the midterm.
It'd be cool if they just copy and pasted.
That would be interesting. Very interesting.
Fingers crossed.
Right. So why I bring this up? Well, you know temperatures, right? You know temperatures. Let's say outside that's way too thin. Let's say outside is 97 degrees, very, very hot. And inside you have a cool, like 80 degrees. Right? No, 85. You have a cool 85 degrees on the inside. And so based on these temperatures, the temperature is going to change throughout the entire wall. You're going to go from 97 degrees Fahrenheit down to 85 degrees Fahrenheit just throughout the entire the wall. Now, why does that matter? Well, y'all remember dew point, right? Y'all remember dew point. That was a fun thing. So let's say relative humidity, 97. Let's say the relative humidity is, say relative humidity, 85.
Do you know if we're allowed to have a psychrometric chart on the test?
It's open notes, so yes.
Just a side comment, in my notes it says on the list of layers, it's one of them is CMU. Would that be like something you would have instead of like a stud as a structural element?
Oh, sorry, can you repeat the question? Something was going on.
In my notes on the list of layers, I have CMU. Would that be another option for a structural element besides like a pine stud?
Oh yeah, definitely. That would probably be under that would probably replace the brick veneer because it's a type of masonry.
Yeah,
And
that's what I was about to say. Yeah,
you
it
still
would not
need-
replace pine studs. It would replace brick veneer, like Edison said.
But if it does replace pine studs, then you're gonna lose out on a lot of insulation unless you put the insulation inside the brick, the CMU, which I don't know how to calculate that. I assume there's a way. Anyway, so actually we're just gonna make this easier on me. Inside's not gonna be 85 degrees. We're gonna put inside to be 75 degrees. Very cold, very cold. 75 degrees. And relative humidity is going to be 60 degrees, 60%, 70%. We're gonna have 70% relative humidity.
Did you come up with that 75-degree number by looking at the chart?
Yes.
How did you do that exactly?
This was just to set up the problem, but well, it depends on the problem, right? You don't go to a psychrometric chart to determine what your internal temperature is. It's based on what you like. So your internal temperature could be 80 degrees, 85 degrees. I just put it at 75, just to make the problem easier. Does that make sense?
Yeah.
All right, beautiful. So now we have these R values, right? You know what's fun about R values? We can use these R values to predict temperatures that will predict the temperature of the wall and every single member and how much heat the wall will take away. So if you recall, R value, it's a measurement of how resistant your material is to heat, right? So if you have a high R value, you have a high resistance to heat. You have a low R value, you have low resistance to heat. So we can use this to our advantage. So I'm gonna make a chart quick. First up, let's add up all these R values.
Yeah, so like when you make the chart, right, like you would have like two columns, like the at the stud, between the stud, and then the only thing that switches is the bat insulation and the pine stud.
Yeah, well, I think what I did is I combined the pine stud and the bat, I think, because it takes up the same amount of space. So I think you would combine them.
Oh, okay.
Well, what do you mean take up the same amount of space? Because I mean, if you're talking about they both take up this area, then yeah. But you said take up the same amount of space, and that's not necessarily true because the
Well, I
pine stuff.
said same space. Well, I meant to say same space, not
Okay.
same amount of space. That's right. So hopefully I added them correctly. 7. Uh, 6 plus 156. All right, so the total R value of this entire wall assembly would be 30.74. 30.74 degrees. Shoot, 30.74. Just 32.74 is the R value of the entire wall assembly. So what can we do with this? Well, you can see there are definitively 1, 2, 3, 4, 5. If you include the air films, 6, 7 different sections, and we have 8 little things. So we're just going to combine the bat insulation and the pine studs into one R value, just to make this easier on ourselves, and that would come out to 18.56 for our R value. Now that's a lot of R value, so we're going to be losing a lot of temperature through here. So what can we do with this? Well, now we can figure out. There are many ways to do this, but this is going to be one way we do it. So the R value, it changes. The R value of the entire wall assembly is 30.74, and then the wall changes. Quick maths, 22 degrees. 22 degrees, right? So there's an overall change of 22 degrees across the entire wall mass. Fahrenheit, delta. And we can actually use this to determine, using the R values to determine how each member would take away how many degrees of temperature. So I think what I'm going to do is I'm going to see exactly how many degrees is taken away per R value, I think. Right, so I'll just divide 30 by 74. I'm going to divide 30.74 by 22, so we have 0.7157. 0.7157. R value. I'm just going to use that as a unit, but it's probably not a unit. R value per degree Fahrenheit. Right. So for every one R value, you would take away 0.7157 degrees.
Good evening, everyone. We're just gonna.
So I don't feel like making a chart because I don't feel like. What's up?
Yeah, let me ask a question real quick. So 30.74 divided by 22, right?
Yeah.
I got 1.39. I feel like I'm doing
Inverse. My bad.
What do you mean?
Wait. I did an oopsie. It would be 22.
Is
Yeah,
it the other
my
way
bad.
around?
The other way around. Oh gosh.
So 22 divided by 30.74?
22 divided by 3.75. Yeah, I knew that wasn't. That
Oh,
didn't
and
look right.
now you get 0.7156.
Yeah. So.
Yeah. Okay.
Yeah. So 0.7157 degrees Fahrenheit per R value. For every time R value is 1. So we have 97 degrees outside. So once the air passes the air film, so you have 0.17 for the R value, right? I'm just going to store this in X to make it easier. Right, so you have 0.17, and you multiply it by this number right here, and then you get, I'm going to move this over here. That's not what I wanted to do. You end up with 0.121 degrees, right? Do the same here. 0.15 times this value, you get 0.07. No, 0.107 degrees. Same thing, this would be 7.16 degrees. Yep. Through the plywood, you would have 0.44 degrees. I use 3 significant values, 0.444 degrees. Once you pass through the bat plus the pine studs, you would get 13.3 degrees. Pass through the gypsum, you get 0.401 degrees. And pass through the inside air film, you would get 0.487 degrees. Right, so what can we do with this information? Well, if you add all of these numbers up, 0.121, you add all of these numbers up, you should get 22 degrees. So the reason why, so that sort of is why we did this little thing and then multiply it all by the R values to keep it proportional, and then you can just multiply it out to get back to 22 degrees. All right. So this is the amount of change that happens that happens because of the member, right? So once you pass through the outside air film, you would lose 0.121 degrees from 97 degrees. 97 minus 0.121. You have 96.9 degrees. After you pass through the brick veneer, you would take away 0.107 degrees from 96.9. You would end up with 90, that's a 6. End up with 96.7.8. It's gonna round. And I think you can see the pattern here. Pass through the polystyrene insulation, you lose 7.16 degrees of inside the air. Minus, you would emerge with 89.6 degrees. Go through the plywood, 89.2. Go through the insulation, you lose 13 degrees. That's a lot of degrees. So you would emerge from that with 75.9 degrees. Emerge from that. Well, once you get through the gypsum board, you would lose 0.401 degrees. 75.5 degrees. And then you emerge from the inside air film, you should reach 75. We'll just double check that. Minus 75.
What does the 0.7157 degrees mean again?
So this is how much the temperature changes every R value, every one of R value. So if you have a wall member that has an R value of 1, then your air would change by this much in this specific scenario.
So U value, is that the U value?
No. U value is completely different. U value is inverse of this, and even then it's a little bit different. U value would be like around like
And so for the U value, that's where we would do the split, the at and between. That's when we would need to split the bat insulation and the pine stud to
yeah,
add.
that's when we would need to split this up.
Gotcha. Okay, here we were looking for the temperature change at each individual level. That was
Right.
okay, got you.
So yes, you would split this up, calculate the R values for at the stud, between the stud, inverse that into the U value. So you have two U values, and then you combine the two U values with your weighted average.
So I guess.
Right. So what can we do with this information? Well, now we can draw a fancy schmancy graph, right? So let me just redraw this wall assembly down here. Just gonna move this over hither. We have our wall assembly. We have that's 1.5. This is 2. Plywood 1/2 inch. It's gonna be around 4 inches or so. Gypsum board.
How did you get to 0.7157?
22 divided by 30.74. So the total amount of change, and then divided by what you want to base your change off of.
Yeah. So that.
Did you get that?
Yeah.
Right. Beautiful. Right. So now we can draw a graph. Right. Fun graphs. Graphs are beautiful. Let's draw some axes. 75, 80, 85, 90, 95. That's draw 6 of them. So why do I draw these axes? Well, right here is gonna represent 75 degrees Fahrenheit, of course. 80 degrees Fahrenheit, 85, 90, 95, and 100 degrees Fahrenheit. So outside, we have outside temperature is 97 degrees. That's around right there. So temperature's gonna penetrate through this wall and emerge as 75 degrees. So obviously you can't just draw a straight line from here to here, right? You can't just like, well, blam. That's not how temperature changes work. If you drew a line like this, you would be assuming that the insulation has the same insulating value as a brick veneer, right? Like that's just not, no, that's not how it works. So we're gonna rather do it smartly. So after you pass through the outside air film, this is gonna represent our air film. It's just gonna be a super light line right there. It's gonna be represent air film. There we go. Right, so after we pass through the outside air film, we're going to reach 96.9 degrees Fahrenheit, and that's not going to change that much. It's going to change only a teeny little bit. After you pass through the brick veneer at 96.8, it's going to change not that much as well. You pass through the insulation, ooh, now we're getting somewhere. Jumps from 96.8 to 89.6. That's a pretty big jump. 89.6. 89. See how big of a jump that is? We'll look back at it later. Now you have your 1/2 inch plywood. Only changes around 0.4 degrees. Now you have your bat insulation and your pine studs. Now how much does that change? That changes 13 degrees. Wow, so much. Jumps down to 75.9. 75.9. 70.9. 75.9. How big of a jump that is. Very beautiful. Gypsum board goes down about 0.4 degrees. And then your inside air film also jumps down 0.4 degrees. Right, so you can see how the air changes throughout here, right? Now, why is this important? Well, y'all remember dew point? Let's just look at the psychrometric chart real quick. So your dry bulb temperature is 97 degrees Fahrenheit. So you just look at your psychrometric chart, you find 97 degrees right there. Just put it right there, whoop lamb. And then you have 70 degrees relative humidity. Right? And then what can you do with this information? Well, you go directly left, and then you find your dew point temperature, which is around 82 degrees. Your dew point is 82 degrees Fahrenheit. Now, at this current climate, with 70% humidity, your water will condensate from the air when the temperature reaches 82 degrees Fahrenheit. Right? And obviously, you don't want water to condense inside your wall. That would be catastrophic. So what you would do is install a vapor barrier to sort of alleviate that humidity from getting in. So 82 degrees Fahrenheit, that's right there. So right at that point, inside the insulation, well, not at that point, but it's an approximation of stuff that will happen inside your wall. So approximately inside your insulation, like around halfway maybe, the temperature will be so low that water will start to condensate inside your insulation. That would do damage to your insulation and do damage to your studs. What do you do to alleviate that? Install a vapor barrier. So what you can do is, let's just say we can put a vapor barrier right here. Nah, just like right there, right there, right there. We install a vapor barrier inside, like in between the studs. Then yeah, we'll be really good. Problem is, it can get even more humid, so it'll fluctuate. Right, so you have to take into account all of that. But for this specific problem, we can put our air vapor barrier right there, right before the insulation, right after the plywood, to sort of just miss that chance of water condensating inside your wall assembly.
Right, it would be like in between pretty much the bad insulation and the polystyrene insulation, somewhere in there. Probably the best place for the vapor barrier.
Yeah, somewhere in here. You can even put it over here. I think that's what they had the wall assembly for the midterm. Yeah, they had the vapor barrier right there. Well, you can overcompensate, you just can't undercompensate. You undercompensate, then bad stuff will happen. So that's what I wanted to go over on Tuesday, but ran out of time because I was too tired.
We're all drained, buddy.
Any questions?
Earlier, when I asked about an air gap, you said that it would have a value of 1. Was that the R value or the U value?
R value.
Okay.
U value is what happens when you take together all the R values. Technically, if you think about it, right, air would have a U value of 1, so you're not wrong. Just not it's not practical. So just R values, take all the R values, you gotta take your resistance, turn it into U, and then move on from there. So yeah, R value of air gaps is always 1.
Right, and I think what Edison's technicality was that because the U value is 1 over the sum of the R value, so if you had just done that single R value, it would be 1 over 1. But realistically, that's not what you do. Like you'd have to add all these multiple R values, right?
Yeah.
Cool. Okay. I just want to make sure I understood that.
Yeah.
Yeah.
So what do you mean by adding all the R values?
Well,
How would that factor exactly in the U value?
that's exactly how you get U. Exactly how you get U value. You know, the equation they give you in class, your U value is 1 over the summation of all your R values, right? So if you were just had your one air gap, right? If you just had your air gap of R value 1 over 1, your U value would equal 1.
Okay,
But that's not practical.
So it's not, so U value is not just 1 over R, it's 1 over the sum of R.
Yeah, the sum of all the R's. You add up all the R's and then U value. 1 over all the R's becomes U value. Does that make sense?
Yeah.
Fantastic. Any other questions? Any questions over like Tech 2, this stuff, like anything that relates to the class?
I have a question about earlier when I mentioned CMUs.
Yeah.
In my notes, you said that the CMU would replace the brick, but in my notes, the ordering of the layers has the CMU a little bit deeper than the brick would be. Does that sound right?
Right.
Well,
wait. Can I ask? Let me answer the question, bro.
You got
because
this.
I see the notes. I know exactly what you're talking about. It was like on March 2nd, and in that notes we had listed 10 different components. So it was outside air film, the brick veneer, the 2-inch air gap, rigid insulation, vapor barrier, CMU, bat insulation, 2x4 stud, gypsum board, and inside air film. Correct? Is that the notes you're referring to?
Yeah.
Yeah, so in that case, it's just like a bigger wall. It's just a larger wall. And then on that same day, we also had another set of notes that only had 7 components, where it was just there was no CMU. But the notes that you're talking about just happened to have 10 components. It just had more in it. You know what I'm saying? So like walls can be different, I guess is what I'm trying to say. And Edison can add on to that.
Yeah, so I had no reference as to, but like from what I could gather, like I assume that CMU would just replace the bricks. But that's for some walls, There's gonna be other walls, and you're just gonna have to sort of adapt to whichever wall assembly you're given.
Yeah, so I think that the notes that we had taken, it was showing us that like the wall assemblies will be different. Like each building will have a different wall assembly. Where sometimes there's a brick and there's CMU and a vapor barrier. Other times there's less stuff. There's maybe only just the insulation pine stud. There might not be any vapor barrier. So it depends on what's given, what's given to us.
Right, and just as a side note, if they give you a vapor barrier, R value is 0. Vapor barriers, R values is 0. And it'll usually like not show up with the thickness, I think. Anything else?
How was your day today?
All right. I will elaborate later. Anything else? Anything about the class? pertaining to the class. Structural, environmental.
I don't know. You want to study before the test tomorrow? One
Sure.
last.
That too. We can do that as well. If you have any questions, that you think up of later, DM me, I guess, on group me. If you have my Instagram, DM me there. Just like you don't have to ask me. Just if you want to, just I'll respond. Right. Well, I'll stop the recording, and we'll be good.